Hello, hello. Shall I start? Hello. Am I audible?
Yes, sir.
Yes, sir.
Okay. So in last class, we have seen why nonlinear activation functions are important in a network and what happens if I use only linear activation functions in a network. So we took an example of one hidden layer and one output layer network with all linear activation functions. So ultimately we found that if I use everything linear, then I learn to of implementation. Okay, so which is just a linear equation. I am implementing a linear equation. So I cannot solve non-linear equation, a non-linear relation. Then I started with last layer as non-linear. Then we solve for this. Then we also found that it is just doing the business of classification and actually implementing a line. So this is also that will not useful to solve linear problem. Non-linear problem. This can solve linear problem. Then we took that non-linearity inside the hidden layer, and then we observe that we can have non-linear, true non-linear relation with respect to input, and we can get a nonlinearity in the output. So these G1, G2s are nonlinear. Then we could observe that non-linearity must be in the hidden side. So that was our observation. Then we stopped there. Then in this class, we are going to see something called as universal approximator. It is, you can say, application of feed forward neural network as function estimator, or we call it as universal approximator, since theoretically we can prove that any kind of function can be implemented with the help of a feed forward network. Any kind of function I can implement using a feed forward network. That's why it is called as universal approximator. Thing is, I'm going to apply a vector as input as usual, and then I'm expecting a function f1 here, f2 here, and maybe fk like that here. So input is x1, x2, xn, and outputs are different functions. Maybe o1 is, say, x1, you can say something like this, x1 square, or you can call it as a1 and a2, maybe x2, and up to an, xn, whatever it is. So this kind of thing, non-linearity I can add, and then I can obtain such kind of relation in the output side. And this may be some other kind of non-linearity or equation. maybe here I'm implementing this kind of function. So whatever it may be. So different kinds of such function I can implement using same input. Now if I choose only one output, then this is my output function. F stands for output function, the function which is implemented by this network. So output depends on this input vector x. Now this f, for the sake of example, I can say this is a sine function. Then if I have single input here, let us say only one input, then O1 is equal to sine of say x1. I want to implement this. Thing is, can this network learn a sine function? For the sake of your choice, you may go for cosine or any kind of such function. Can this network learn? That is the question. So what we can do is, we are, suppose I am doing tan, I am doing suppose sine, then I am going to use nonlinear activation function here and here. Let us say tan h. Okay, so output will be in the range -1 to +1. Okay, output here will be in the range -1 to +1, and relation between input x1 and output O1 is sine of x1. O1 is equal to sine of x1. That means if I supply here say sine value, x value, then corresponding sine value will be thrown out. Okay, so to do this, to learn such kind of relations, what we are going to do is, we are going to take say a sine wave. You will do this in practical. Say this kind of a sine wave. Suppose this is my sine wave, then I'm going to sample this sine wave at regular interval. And this pair of, say here is my input. This x-axis will be say x1, and this is sine of x1. So all these x1 values and corresponding sine x values, they will be forming training data. So training data is of this form. So maybe 0.1. So this you can take in radians. 0.1, then maybe 0.2, so on. Then you can take corresponding sine values here. So this will be my input for the network, and this is my desired response. Now earlier you have observed that I was supplying x with a desired response. So this pair is training sample. Now this used to Earlier used to have values plus 1 and or minus 1. Now instead of this binary outcome, I was representing plus 1 for say class 1 and minus 1 for class 2. Instead of that, I am going to use D as now sine of x. That is my desired value. I will be supplying you x, and this feed forward network will throw out say sine of x. Okay, that is say my aim. So what I do, I just take the sine wave, then I just sample it at regular interval, and then I make such kind of a table. And then I use this architecture. Here only one input is available, and this is fixed connection bias. And suppose I use say 6 to 7 neurons here, and then one neuron at the output. I randomly assume this V matrix here and a W vector here. Once I do that, then I will be say attaching here 0.1, and for that I will have a desired response corresponding sin x value. Then I take another sample, maybe 0.2, then its desired response is sine of 0.2. So this value, this number will be my desired number. Like this, I may have say such 10-20 samples, and then I will try to train this network. Okay, then this network will be trained again using backpropagation. Same thing, same formula, only thing is desired response instead of plus 1 minus 1, it will be in the range minus 1 to plus 1. So if that is the difference, rest thing is same. You can use same classification program here also. Thing is, you will be now using tan h functions for hidden layer as well as for output layer. Now you can see result here. This, suppose this was my training sample, and then cross is my training result. Then you can see diamond was my training sample and cross is my training result. So they are matching perfectly. So you can, if you join this, it becomes a sine wave like this. So hardly there is an error in training sample. So training error is approximately equal to 0. Now in next step, what we are going to do is we are going to take a sample which was not shown to the network during training. Suppose this is my sine wave and I took these two samples, then intentionally I will be choosing this middle value for test purpose. For example, I started with 0.1, 0.2, then this was used for training. Intentionally, I'm going to use 0.15 for testing and check whether my network produces sine of 0.15. It will produce some value, and I'm going to check with its actual value, and that will be my error. Now if I do with say 5 6 neurons, you see that this diamonds here are actual samples, say like this, and that is the corresponding real value of sine. You will see that for this sample it is producing this value as sine, which is not correct. So this much is error. So like that, if you see closely, this cross is the test result, and it is not matching to the actual value. There is error here as well as here. Whereas training was perfect. It was perfectly matching with training sample, but for test sample, it is not matching. So test error is not equal to 0. There exists test error. That means network has not learned to the desired level. However, network has learned the training samples. Now what we can do is we can increase hidden nodes. By increase hidden nodes, then you will see that better results are observed. Okay. So if you write a program like this, you can try with different combinations of neurons. So I think 10 neurons are sufficient to get a proper sine function. So this is about the function approximation. Sometimes it is called as regression. So you can try for different kinds of shapes and you can learn different functions. However, note that our aim is to learn different functions, not the standard functions. So if you give me x, then I can give you sine of x. That is, there is no fun in doing this. I'm not interested in doing this kind of things using neural network. I'm interested in the real world, like if I give you stock exchange data, maybe this kind of data throughout some period, say period 0 to period suppose n, and then these are the corresponding stock values. And if I give you this data for maybe last 10 years, thing is, can you estimate based on this data what will be next value, or what will be tomorrow's value, or such kind of shapes I want to learn, such kind of functions I want to learn. It may be coming from any kind of physical phenomena. Okay, so I want to learn such kind of functions, not this standard function. So if I want to do like this, then I will be preferring neural networks. Okay, I will be using neural networks for function estimation. So that is a small application of neural network. Then next point we are going to cover is the associative memories. So this is similar to our brain memory. The basic concept is I will be supplying you a vector x as input, and that vector x will be mapped to vector v as output. Note that here dimension is n and here dimension is m. So my input vector is n dimensional, output vector is m dimensional. So I want to learn this association. I want to learn the association between x and v. So this is my pair. If I supply you x, you will throw out v. If I supply you say x2, you will throw out v2. So such kind of pairs I want to remember. Now what is the application of that we will see subsequently, but concept is say x1 is input, v1 is output, x2 is input, then v2 is output. Like that I will keep on learning maybe n number of pairs, and this I want to remember. Okay, that is the basic concept of memories. This is not same as memory of a microprocessor. So what you do in microprocessor, you supply some address, then there is address decoder which decodes what you want to read or store, where you want to store. That is given to a memory chip, and your data is arranged in this form. In that particular row is selected, your data is written over there or it is thrown out. So I supply some address and then corresponding data is thrown out, or you can write there. So this is your normal memory, but our brain is not working on this principle, right? There is no address in your brain. Can you tell me where your name is stored in your brain? Is there any address for that? I don't think so. There is no such kind of addresses in your brain. It works on different mechanism. So we are trying to do that kind of, we are trying to implement that kind of mechanism where input is a vector, output is another vector, and there won't be any address as such for recalling the things. So you can see these are suppose words, they're stored like this, and you have data input, and then it will throw out corresponding data out. Now, types of memories that we have in artificial neural network. The first one is very simple, feed forward. You will supply input xk and then corresponding vk will come out. Then there is a feedback kind of network. You will supply say x0 for timestamp x, say timestamp 0. Then it will be producing some output. This output will be fed back to the network, and this will be iterating. We will iterate till the network settles. Once it settles, this will be my corresponding output. So such kind of mechanism is feedback. Okay. Now this feedback has you can say two types. A network which is called as auto-associative memory or auto-associative is mapping say x to x only. The dimensions are same. Okay. See, here you can say x0 and vk plus 1 has same dimension, x1 x2 up to say xn. Similarly, say vk plus 1 will have same dimension. They are having same dimension. So if that is the case, then you are doing auto association. You are relating x to x itself. There is nobody involved. A vector x1 is mapped to x1 itself. A vector x2 is mapped to x2 itself. So input is x1, output is x1. Then what is fun of doing this? So we'll see one example here in next slide. Time being, you take another example of feedback network, which is heteroassociative. Here, input is say vector x1, and then output is vector v1, but dimension of x1 is n and dimension of say v1 is n. They are not same. So we have here that way two matrices. One maps x1 to v, and then we take another feedback loop from v to x, and this is iterated over a period of time, and when network settles, output is thrown out. Okay, so why this recursion is required, that we will see in subsequent lectures, but try to understand the mechanism. In normal neural network that we have seen for classification, we apply input, then we have different classes over here as my output. So depending on number of classes I want to learn, I will be keeping say output terminals equal to say k, and k is number of classes. So this is normal thing in a feed forward network. There is no feedback in feed forward network. Name itself is saying feed forward. There is no feedback. Similarly, in the first type of memory, I have only feed forward. I will put something in and then I will take output. There is no feedback. There is no loop. But this adds some limitation in case of memory application. So what is done is we feed X, we take output, and then this output is again feed back as input, and then again new output is completed. This is again feedback, and then when there is no change in the output, I take the final output. Okay, so that is the feedback mechanism. So there are two types, as I said, auto association and hetero association. Now this is a good example of auto association. What this network has already been trained is to learn 4, and output is 4. So if I apply 4, it produces 4. So as such, there is no fun in doing this. But see the application. Here I have a distorted input. Distorted 4, if I give to this network, then this network will do the correction and throw out this kind of say clean version of 4. Okay, so distorted input is corrected and you get a clean version. So this is possible with the help of auto association or self association. Now this is hetero association. Say this is input to the network, which is an image of a plane, and then this image is fed to the network. Network iterates, and then it produces this plane as output. It takes image as input and produces text. Corresponding name of the object is thrown out. So if I take this image and fed to the network, then it throws out tank. See, maybe this is copter and so on. So I can relate different vectors, different size of the input vectors. How this is trained? So what we do is we take the first column of an image, then we attach this second column of the image, and then we attach third column, and we keep on doing this till last column. So this becomes my column image, and this is the input vector x. I know the dimensions of image is suppose n by n, then I know these are the different columns of the image, and this will form x. Similarly, I can make I can collect all the columns of this plane and then form a vector. So this is suppose v vector and this is x vector. So x is then mapped to v. So like this training will happen. So I will take this big X and then I take this V and I try to establish a relation within this memory. So whenever this network sees an aeroplane, it will throw out text as plane. Whenever it sees tank image, it will throw out the text tank on the output side. So since input and output have different kinds of dimensions, this is called as heteroassociation, whereas this earlier association is of the same image to same image. So this is 4 to 4. So while training, we'll be giving clean image as input and then clean image as output. So what is expected from network is, even if I give network a distorted version of 4, it should come up with clean version of 4. That is application of auto association. So the first kind of network is the linear association or linear associator, which is feed forward network. Here we will see how I can store different associations. So this is my vector x applied as input, and then this is the corresponding v produced by the network. So x is mapped to v. This I want to implement. So what I'm going to do is, why this network is called as linear, because it has only linear units. So you see the activation function, these are all linear functions. That means f of net is equal to net. So on suppose x-axis I take net, and then on y-axis if I take f of net, then output is same as input. So the relation is like this. So that is what is indicated here. Whatever is net coming here will be coming as output on this terminal. So net here will come as output here. Okay, so we will see how such kind of network can remember this association between two vectors. Note that input dimension is n here and output dimension is m over here. Okay. Let us assume we need to store p different associations, and S is stimulus and F is forced output. So S stands for, say, input, and suppose F stands for output, and there are such p number of pairs I want to remember. So suppose I take Si as a generalized input vector, then Si consists of S1, S2, Sn, n number of values. Okay, so similar to that, F is my output, forced output. Stimulus is stimulating the network, and then because of the stimulus, F is produced. So this is my input S, and this is my output F, and this is linear associator. Okay, and these are the corresponding individual values in F. Now see, we are going to use Hebbian learning rule. So this is the first time we are using it in a network. Till now we have seen perceptron, delta. Okay, then we have seen in one network winner take. If you recall, I have said that we are going to use Hebbian in memory networks. So here we are using Hebbian to obtain the weight matrix of linear associator. So all we do is say W prime ij is equal to Wij plus Fi Sj, Fi into Sj. So this we are going to do for I equal to 1 to m and j equal to 1 to m. If I do this, then I am implementing Hebbian learning rule. How do I say like this? Say this is my linear network, suppose like this, and this is suppose input coming to neuron 1. Okay, so this will be W1 1. So this is S1, maybe S2, and you can call this as S3. So this will be W1 to W1 3. Now suppose I want to do updation of W1 1, and this is the output of neuron 1. Then if you remember, change in weight for Hebbian is COX. If I want to do change in weight for the first weight for a neuron, then C, suppose I take 1, output for first neuron is O1, and then for this particular connection input is say X1 or S1 in this case, and this weight I will call it a W11 because it is dealing with first neuron and first connection. So this O1 into X1, here it is F1 into S1. If I go for this connection, this will be O1 S2. For this connection, this will be O1 S3. And suppose there are so many such S up to maybe Sn, then I will be doing O1 Sn. Okay, so this I will keep on doing for different kinds of weights of neuron number 1. Then I take neuron number 2, and I just want to use same thing, same rule to update those weights. So here it will be W, suppose 21, then W 22, W 23. Okay, so like that I will be doing O2, say S1, O2, S2, O2, S3, and that will be added to earlier weight. Say W21 old, W22 old plus W23 old. So this will be implementing Hebbian learning rule for my network. Now this you can do very easily instead of doing like this by a method called as outer product. Okay, that we will see. So this generalized step to obtain weight change due to one pair is done using outer product. So W prime, this is new value of weight, and this is F S transpose. So this is F, suppose 1 F2 up to Fm. This will be multiplied with S1 S2 up to Sn. So this is not a normal product, this is not an inner product, this is outer product. So this will be equal to F1 S1, F1 S2 up to F1 Sn. Then F2 S1, F2 S2 up to F2 Sn. Like that you will go up to Fm S1, Fm S2, Fm Sn. So it will be forming a matrix. So this is nothing but your weight matrix of linear associator. So this is due to training sample, say number 1. I will be doing same procedure. I will be constructing similar matrix with training sample 2. I will be doing same with all n samples or p samples in this case. And then we are going to add all these p weights to get the final weight, W prime or something like that. And this will be used for linear associator connections. So more on this we will see in next class. Time being you can read this from Zurada's book. Okay, I will repeat the steps again in next class. Thank you.